Prior to the study, it was known that a large section of ventral cortex activates in response to objects and shapes. It was also known that ventral temporal cortex encompasses face-selective, body-selective, and scene-selective regions. Most other object categories, like shoes and cars, for example, activate a large portion of occipitotemporal cortex. Finally, we know that ventral temporal cortex shows activation in different areas with animate and inanimate objects. There are a few areas in the literature in which gaps existed prior to the study. Researchers wanted to understand the nature of the responses to objects and how they are organized. The role that size plays in brain activation was also unclear. The research question of this study was, what is the nature of object representations in the brain? The researchers wanted to understand the nature of the object responses and to determine if there is a large-scale organization to object categories. They hypothesized that object representations may be naturally differentiated by their real-world sizes and would be reflected in a coarse spatial organization across occipitotemporal cortex.
In the study, there were 22 observers with normal or corrected to normal vision. 13 were female and 9 male, and there was an age range of 19 to 36. Each subject participated in a 2-hour session where they took part in one or more of the 3 fMRI experiments. MRI images were all collected on a standard strength 3T fMRI scanner. Experiments 1 and 2 used a 12-channel phased array head coil, and experiment 3 used a 32-channel coil. For all experiments, the field of view was divided into a 64 by 64 matrix. There were 32 axial slices per imaging volume with a voxel resolution of 3.1 mm cubed. The bulk contrast was done using a gradient echoplanar T2 star sequence. The time to repetition was set to 2000 milliseconds and the time to echo was set to 30. The first experiment looked at the general effects of viewing small versus large real-world objects, where all object images were presented at the same visual angle of 9 degrees. As you can see, the experiment used a standard block design. Each block of small objects, as shown in light blue, or large objects, shown here in dark blue, lasted 16 seconds. Within each of these blocks, a total of 20 images were shown for 500 milliseconds each, with a 300 millisecond blank between each item. Then between stimulus blocks, there was a 10-second fixation period, shown here in grey. In a single run of 8.8 minutes, 10 blocks were presented for each condition, which meant in total there were 200 distinct objects of each size. To maintain attention, subjects were instructed to press a button when a red frame appeared around an item, which only happened once per block. Experiment 2 looked at the effects of retinal size manipulation of the 2 real-world object sizes. Observers saw a total of 4 conditions, small and large objects presented at both small and large retinal sizes. The objects, block design, and attentional instructions were identical to experiment 1. For the large retinal size condition, small and large size objects were both presented at 11 degrees visual angle, shown here in the purple and dark blue blocks. For the small retinal size condition, small and large objects were both presented at 4 degrees visual angle, shown here in the light blue and teal blocks. To reduce carryover effects, the 4 conditions were presented in a random order, which meant each condition appeared at random only 5 times per 8.8 minute run. The final experiment examined the effects of mental imagery of small and large real-world objects. The names of objects were presented to subjects orally while their eyes were closed, and they were then instructed to form an isolated mental image of that object. The experiment used the same standard block design to the first 2, except here the 16-second blocks contained only 5 object names. Blocks of stimuli were followed by hearing the word blank to signal the 10-second fixation interval. The experiment involved 2 separate runs. In the typical run, subjects alternated imagining small and large objects at their real sizes. In the atypical run, subjects alternated between imagining small objects as giant and large objects as tiny. Each run contained 3 blocks of each size condition and lasted a total of 5.4 minutes. The study used a medium-length block design with a baseline fixation because this length provides clear time courses and lets you model stimuli conditions individually. The visual task in experiment 1 was chosen to simply contrast the organization of large and small object preferences in cortex. The retinal manipulation and mental imagery tasks in the second and third experiment were chosen to test whether the identified regions of interest maintained their object size preferences in new contexts. All tasks use a blank screen fixation as a baseline measure of neural activity, which helped distinguish activations from deactivations. Before any statistical analysis, data was pre-processed using Brain Voyager software. First, there was slice scan time correction to account for the fact that functional slices are collected in an interleaved order. Then, subject head motion was corrected for along 6 possible parameters. Then there was linear trend removal, which removes the drift in bold response over time. Then a temporal high-pass filter was applied at a frequency of 0.01 Hz. This allows high frequencies that represent signal to pass into the data, but filters out low frequencies that represent scanner noise. The activation was then spatially smoothed at 4 mm to increase signal-to-noise ratio, which thus increases the chance of subjects' activation maps overlapping. Finally, results were transformed into an average brain using standardized tau rate coordinates. Statistical analysis on Experiment 1 data used the general linear model. A whole brain random effects group average analysis was conducted, which transforms all subjects' activation maps into a single stereotaxic space. Therefore, it gives the average results for object size preferences in cortex. A contrast was conducted at the significance threshold of 0.001 to test for brain regions more active to small versus large objects, or vice versa. Regions defined from these contrasts were used as regions of interest in the next analyses. ROIs are defined as the set of adjacent voxels that are significantly activated around the peak voxel in a restricted part of cortex. Contrast of small over large object preferences identified occipitotemporal sulcus, or OTS, and lateral occipital cortex, or LO, as the small object regions of interest. The opposite contrast of large over small preferences identified parahippocampal gyrus, or PHC, as the large object region of interest. For each ROI, general linear models were then run on the average time series of the voxels within it to obtain regression coefficient betas. Because experiments 2 and 3 were 2x2 designs, repeated measures ANOVAs were then run on the beta coefficients across subjects for each ROI.
The key results that were observed in this study can be summarized by the following. In Experiment 1, big to small object preferences were found arranged from the medial to the lateral surface across both hemispheres of the brain, where big objects were associated with greater activation in the medial areas, and smaller objects were associated with greater activation in the lateral areas. 3 areas of significant differential activity were identified. The parahippocampal gyrus area that responded optimally to big object stimuli, and the occipitotemporal sulcus area and the lateral occipital area that both responded optimally to small object stimuli. In Experiment 2, all of the areas showed greater activation to objects of preferred real-world size regardless of retinal size, when the retinal sizes of the objects were manipulated on screen. However, it is worth noting that the big parahippocampal area also showed a significantly greater amount of activation to retinally large stimuli, meaning there was a main effect for both preferred real-world size and retinal size in this area. Finally, in Experiment 3, the results remained consistent even when the objects were imagined using mental imagery rather than projected. The area preferences remained the same for real-world sizes, regardless of imagined size.
The main reason these results are important is because at the time there was no evidence to explain the general large-scale activation to objects in ventral temporal cortex, aside from the animate-inanimate distinction. Inanimate objects are physical entities, so their size in the real world is an important defining property because it determines how we interact with them. Additionally, specific size preference regions, which retain their preference during changes in retinal size, were still activated during visual imagery, and were activated regardless of the size of the imagined object. This reveals that real-world object size preferences in cortex cannot be explained purely by low-level retinotopic effects, nor by high-level abstract conceptual effects. In fact, it suggests that size preferences in cortex are based on features like object category and visual form. The object preference regions identified in this paper overlap with areas already well understood in the literature. Big PHC overlaps with PPA, which is known to respond to particularly large objects and strongly contextual objects. The small LO is located nearby and partially overlaps with areas such as functional LOC, EBA, MT, and the medial temporal gyrus tool region. One researcher previously found that category-selective regions come in pairs and are mirrored across medial ventral regions.
One potential issue with the methods of this study had to do with the distinction between big and small objects. The criteria for an object being considered either big or small was never clearly outlined. Another potential issue of this study has to do with the ROI approach used for experiments 2 and 3. Although the ROI approach provided the study with greater power, it also created the opportunity for important areas of significant activation to be missed in experiments 2 and 3.
Future research would have to investigate evidence for both the experience-driven learning about the relationships of object size to eccentricity and the connection between object size organization and downstream action requirements.